Good morning, everyone. I hope you're doing well today. As I announced, your test number 2 is available on Blackboard, just as it was for test number 1, same format. Again, the same window of time. So you have basically today and tomorrow by 11 p.m. Friday, which is tomorrow, the test is due. And then, of course, for the test work, that's done the same way. I'll just remind you, you scan your work, you create one file, and you have the 30 minutes to upload the file where you go to the test work number 2 tab. It just says test number 2 work, and you'll use the Turnitin app. Remember, that's a really essential part of the test. It's kind of like you're in a classroom and you finish your test, gather up your books and everything, and you walk to the front of the classroom and pass your test to your professor. So that's the Turnitin aspect. And so it's a very critical part of the test. And so again, one file, that will be a requirement. There are no exceptions. The test must be completed by 11 p.m. And then, of course, I give you that cushion of time to upload your work. And again, that's a seamless strategy that I think is very appealing to everyone. Again, remember, my focus is to give you enough flexibility to do the test so you can negotiate all the other obligations that you have. So every aspect of the test is set up to be fair. So again, take care of that. And then, of course, you'll have some time with your spring break, which I'm sure you will enjoy, to get a little rest and maybe do some extra studying. Again, I also have my sessions today, conference hours. I will send invitations out for those. So take advantage of those if you would need them. And then, of course, I have a session tomorrow morning, same as usual. Again, I will also be checking the WebAssign if you have additional questions or whatever. So the setup is just like the first test, so no kinks, nothing to be confusing. So I wish you well as you embark on that. Now, today, what I wanted to do was just basically do some review problems. Again, a lot of you are probably yawning. It's like, well, I know how to do all of this, Professor Ron, and maybe you do, but that's okay. I want to highlight some problems that have been asked during the conference hour that I think are very good problems from WebAssign. And then I'm just going to do some spot problems from some practice tests that you have on Blackboard. So let's get started. And good morning to everyone. I appreciate your comments. Very nice. So one question that has come up quite often during the conference hour is just one of your WebAssign problems. And it actually can be done a couple of ways. And some of you are very familiar with this already. You can probably listen to some music while I do this. And it's an interesting problem. Again, WebAssign gives you a hint, and then, of course, you can use another method, which, of course, is a little bit longer if you use the definition of logarithm. So the way this is set up, we have x minus 1 as a base. And so we just want to, let me just write, solve in the real numbers. Solve in R. So this is one of your WebAssign, and there are actually 3 examples with this, and I'm going to do a couple of them that were asked several times. So if you look at this, we have a base of x minus 1, we have a power of the base 10 log of x minus 1, and then, of course, we have 100 times x minus 1. Now, the thing is here is that these bases aren't the same, so it doesn't collapse. But you can see that the power of x minus 1 that equals 100 times x minus 1 is log of x minus 1. So log of x minus 1 is indeed a logarithm. So this is kind of like, all right, I can use the definition of logarithm. Well, WebAssign says, why don't you just take the base 10 logarithm of each side? And so as some of you have asked on WebAssign, I've said you can use the hint also. So you have two ways to do this problem. But what I want to do is use the definition of log so we can actually practice changing the base, because we're going to have two different bases to work with. So again, equivalently, a logarithm is the power of the base. So log base 10 of x minus 1 is actually the logarithm base x minus 1 of 100 times x minus 1. So what's a logarithm? A power of the base. So this works just like we've always done. Some of you sometimes say, I don't quite get this. And then I say, then you don't understand the logarithm. What's a logarithm? It's a power of the base. You should have learned that in college algebra, but that's okay if it's gotten rusty. That's why we review this. But with that said, I love this problem because it highlights all of the essential details. And then as we work other problems, you'll be like, oh, I get it now. So notice here, this side is fixed, but we can apply the product rule here. So we have the base x minus 1 log of 100 plus the base x minus 1 log of x minus 1. And of course, this is the base 10 log of x minus 1. Now, before we decide to change one of the bases, because we know we can't really use the logarithm definition in a continuing style if we have two different bases. But notice here, what's a logarithm? It's a power of the base. I know I sound like the broken record, but I'll be a broken record because some of you still don't understand it. So when we see here, we'll say what power of x minus 1 equals x minus 1? Well, the first power, okay? So that's 1. That's just 1 by definition. And so we'll write everything, we'll just do everything in one step and spread it out. I mean, one step for each process. We're not the problem in one step. That would really be kind of useless, right? So now when we look at this, just imagine that maybe this is a base 10 and that's a base 5. We have a base x minus 1. And so the bases are different. So what we would do is just choose the fact that we like base 10 because it's easy. So we'll say change base x minus 1 to base 10. And what's nice about this is that, like I said before, we get to use all of the nice properties of the logarithm. So we have the base 10 logarithm of x minus 1. Now we'll change to base 10. So that'll be log of 100 divided by log of x minus 1 plus 1. So now you're thinking, oh, we're going to end up with a quadratic equation in log of x minus 1 when we cross multiply, or just clear the denominators. So that's the key. When you take the base 10 log of each side, you see that result quicker. But again, I want to go through this to highlight some of the important properties of the logarithm. When you get to calculus 2 and you start doing integration techniques, you will see logarithms all over the place. You will see the quotient rule, the product rule. I mean, you will use these concepts over and over as you learn them, relearn them, and bring them to a new level in calculus 1. So these constructions that we're doing now will just live with you forevermore if you stay in STEM. And of course, that would require you to do mathematics. So now we have an easy problem. The base 10 log of 100 is 2, right? The power of 10 that equals 100 is 2. So we'll go ahead and reduce that. So that's 2 log of x minus 1 plus 1 equals log of x minus 1. Even if you've seen this problem worked before, it's always good to work it again. to really understand the problem, when you're younger, and you all are like 5 years old, I mean, compared to Professor Ron. And so you just work a problem 5 and 6 times. You teach it to the wall. You teach it to your pet bird. You teach it to your mom and dad or your aunt, your uncle, or your best friend, just to give an opportunity to talk about what you're doing. It does make a difference. So now we're like at the first week, we want to clear the denominators. So we're going to multiply both sides by the log of x minus 1. Do the same here. So we often try these algebraic techniques to convert the equation into something we understand. So now we have 2 copies of the logarithm in the square form. So we have log of x minus 1 quantity squared. And here, of course, just like we do symbolic computation, the log terms absorb and we're left with a 2. And then, of course, 1 times log of x minus 1 is just log of x minus 1. So this is the beauty of this problem. As I've always said on the test, I will ask you to solve problems that can be computed via these techniques. You won't need to worry about a problem that'll come up that you would need approximation techniques from calculus to do. So I'm going to focus on the problems that you can solve with the techniques I've taught you. So now we have the square term, the linear term, and the constant. So we say quadratic in the base 10 log of x minus 1. And we like that. Why? Why do we like that? Because we know everything there is to know about quadratic equations. You'll be ecstatic in calculus when you end up with a quadratic equation. You'll be like, well, hallelujah, I can finish this problem. So now what do? We remove everything to one side and then try to factor. And of course, the author was very good to us with the factoring. So here we take this over. So this will be a plus -1 times log of x minus 1 minus the 2 equals 0. So what I want to do here is kind of focus on the fact that this is the squared term, like the x squared and the x, and the coefficients here, 1, -1, and -2. So some students have said, well, do we need to do a substitution? And I'll say, no, it's clear what the expression is quadratic in. So that substitution is just maybe a symbolic gesture, which really doesn't move the problem forward and actually adds more clutter. So, like I say, I told the students at the time that my understanding of substitution has to be something that truly pushes the problem forward. If you have to do that just to go backwards, nothing has been accomplished. So now notice AC method, AC, so that's going to be what? 1 times -2. But yay, 1 plus -2 is -1. So we don't even, well, I don't even need to do an equals. Just say AC equals. Sometimes I just look at it and say it's -2, but if you write the AC as I've taught you, then you get the proper sum here. So you know this factors via Professor Ron's AC lemma. So we have log of x minus 1 minus 2 times log of x minus 1 plus 1. So I'm thinking if you can do this problem, there's not a single problem I could put on the test that would even trip you up. So now we're like, okay, so we're back to week 1 of pre-cal. We have 0 product. So the product of these 2 expressions is 0. So we know at least one of them must be 0 because these are real expressions. So if and only if, we would have log of x minus 1, base 10 log of that equals 2 if we transpose. So set this to 0. So this says base 10 log of x minus 1 equals 2. Or set this to 0, base 10 log of x minus 1 equals -1. Okay, so now what's the logarithm? Well, it says the power of 10 that equals x minus 1 is 2. So this says x minus 1 equals 10 to the second power. Well, we remember that right back up here, right? We've already done that computation. But 2 to the 10 is 100. So if we add 1 to both sides, we get a value here at least of 101. Now the same thing here, the power of 10 that equals x minus 1 is negative 1. So x minus 1, so we're writing the equivalent exponential is 10 to the minus 1. And of course, we can just write that using the definition of minus 1 power as 1 over 10. So now we can add 1. Now, of course, 1 is just 10 over 10, same denominator, excuse me, and 10 plus 1 is 11, so we get 11 over 10. Now, of course, we know that the logarithms possess really very elegant identities, and you will use those, like I said, again, in your calculus sequence. So we need to make sure that at least what we have here does work in the original equation. You'll find when you do calculus techniques, you'll use that quotient rule, and depending on how you write things, certain things won't be defined. And so calculus 2 students are always playing the routine of like, oh, can I write it this way? And of course, WebAssign will read things with numbers in them as an equivalent identity. And so you can sometimes get away with something that looks odd or undefined and actually get the right answer. But I always remind my students, please don't write things down that really just don't make sense. So now here, when we see the 101, we see that, of course, the logarithm is defined there. That's a positive input. And then, of course, 11 over 10, subtract 1, that's still a positive input. So we see that the original equation is preserved with these values of x. And so this gives us 2 legitimate solutions. That is, we have 101 and 11 over 10. Now, of course, I encourage you to do this problem just by taking the base 10 log of each side and proceeding that way. Again, I chose this method because I think it highlights so many of the nice details of the logarithm function, and that's a good thing. Sometimes a problem that just makes us think about all the particular characteristics of a function is the most useful. Okay, now another example that was also asked, let me go ahead and do that one. So this is a good practice. Just once you finish studying, complete your WebAssign, just work it a couple of times, help a friend with it. Now, the other problem, there's also a nice half-life problem that was asked. Of course, I use these as, a sign that this might be a problem that everybody would have, as far as something that they may feel that they need a little extra push on. And so the other example was this: solve in the real numbers. And this one had this form, 4 to the x minus 2. So we're now focusing on exponential functions and then all the qualities that they may possess. So like when you saw the last problem, you looked at it and thought, well, there's some clutter here. What do I do with it? Okay, well, again, follow the hint or use the definition of logarithm. Here we're thinking, or we're at least hypothesizing, we've got 3 terms here. And so maybe just like the last problem, it would be a quadratic equation. Now notice, and this is an important point here, we see that we have a base of 2 here. And then of course it's times 2 because we have a plus 1 here using the laws of exponents. So the idea is we would want to maybe try to convert the other term to the same base, which I think you can see we would be able to do. So we can observe the fact that 4 is actually the square of 2. Now that may be very simple, but it's important to solve the problem. So again, what do we do in mathematics, ladies and gentlemen? You know, like we learned the unit circle, or we learn about the logarithm identities. We write the problem in a different form. We write the problem in a form that will bring to light some pattern or some construct that we understand. Okay, if we have an input to a trig function and it's got a bunch of multiples of 2 pi in it or pi, we're going to get rid of them. Okay, we have to set up the problem to a simpler form. And then of course, what basically is that? It's just recognizing patterns. So when a lot of you say you want to do computer science, I said, great, because mathematics trains you to recognize patterns. And when you do coding in computer science, that's really all you're doing. You're trying to create algorithms that are efficient. And of course, working with the computer language is like working with the language of mathematics. You have to learn all the key words, so to speak. So now we can replace 4 with 2 to the 2. So we get 2 to the 2 for 4, which is raised to the x power. And then of course, 2 to the x plus 1 is 2 to the x times 2 to the 1. Put a little dot there if that helps the understanding. 2 to the x times 2 to the 1. Laws of exponents. And then of course, the 3 here, we can just bring over, subtract 3 from both sides. Now, again, let me just remind you, for instance, when we have a to the x times a to the y, that's a to the x plus y. So we actually work this identity this way, backwards. And then, of course, if we have a to the x raised to the y, this is just a to the xy. So now, if we look here, we're thinking, okay, there's nothing wrong with interchanging the x and the 2 here. The multiplication of real numbers is commutative. So let's just interchange these. And this will be 2 to the x quantity squared. And now, of course, we have 2 times 2 to the x with a negative sign. So we can say plus negative 2 times 2 to the x. So what we want to do is dress this up just like we did the last problem. And often what I do to make it very clear is that this is the coefficient of the non-squared term. And of course over here, we just have a 1. So this is a quadratic equation, just like the previous one, but now it's quadratic in 2 to the x. So we say quadratic in 2 to the x. So not only in this class is this useful, but this will be useful in future classes in mathematics and STEM. So now, again, we can do the same thing we did before. We've got quadratic in 2 to the x. Let's check to see if we can get a simple factorization. So, well, let's do a little sidebar. We'll write this over to the right so we don't interrupt the flow of the problem. So we have AC, in this case, is 1 times the negative 3. But of course, that's really good because the sum of these two factors gives us the negative 2. So that's a check, all right? So as I've told students during my conference hours, if this doesn't work, then you can still always use the quadratic formula. And then of course you have 2 to the x equals the minus b plus or minus the square root of b squared minus 4ac divided by 2a. You just have to do the extra work. It's still accomplished. The same techniques are accomplished. It's just that it's really nice when we get a really interesting, convenient factorization. And of course, the leading coefficient is 1, so we don't even have to work hard to factor this. So this is 2 to the x plus 1. And then we have 2 to the x minus a 3. So again, just like before, we get the minus 3, we get the 1, so we get the -3 copies plus the 1 copy gives us the -2 copies, and then the square. The thing is that when you see the 2, you think 2's the coefficient, but again, 2 is the base. That's why I put the parentheses here so you can easily see. And if you like, you can just go ahead and do this. So we square 2 to the x. Here, this is the first power. Here are the coefficients, so it's just like a standard quadratic equation, but you need to take a little bit of time to dress it up properly so you can see everything and just match everything up. Again, achieve the pattern. Now we have zero product, so we can set each factor to 0. So that means we just set this to 0. So 2 to the x would equal -1, or 2 to the x equals 3. Now, of course, we know that the base A exponential is a positive output function. So this would have no solution. It would not be possible for an exponential function here to have a value of -1 unless there were some negative coefficient over here to absorb it, and there isn't. So, of course, you can try to apply the definition of logarithm, then you have the base 2 logarithm of -1, which is undefined. So we'll have, in this case, no solution. So we don't get any contribution from this particular factor. Okay, now here, of course we will. So now we look at this and say, well, the power of 2 that equals 3 is x. So x is a logarithm. So if and only if x equals the base 2 logarithm of 3. So again, here, this would be a legitimate solution. This solves the original equation. The exponential equations are very flexible because the inputs all real numbers. The only thing that we'd have to worry about if we had some rather exotic powers that might eliminate some real numbers, but we don't have that. Now, of course, this is a legitimate solution. And then if, WebAssign or the test said, write your answer in terms of natural logarithms or something, occasionally you'll have a problem where we always get an exact solution, and then the problem says round to a certain number of decimals or no decimals. And so what we want to do is we want to produce an exact solution that we can easily approximate with Google. And again, we want a nice, clean approximation because we have done no approximating to that point. Okay, so now, of course, if the problem requested an answer in terms of natural logs, we could just change to the natural log. So we'll take the ln of 3 divided by ln, in this case, of 2. So remember, if we have base 2 to change to base e, we just take the base e of the argument 3 and then divide by the new base of the old. So this would be another way to actually write the solution. So either of these would be equivalent. And then, of course, if you were selecting an answer, you would need to find the one that was equivalent to one of these. So again, when we write our solution, I'll just do it with the base 2 log of 3. Again, don't overthink, but don't underthink. The idea is that if you fear making a mistake, you don't move forward. So it's better to just go ahead and work and then assess, just like you do on your quizzes. And the test work, again, is my way of seeing that you understand the logic. So again, just like I do in class and lecture, we work based upon the recognition of patterns. And then, of course, we apply techniques that we have learned in class. That doesn't mean we shut down our intuition and our common sense. Of course, we always apply that. And that's something in mathematics that is indispensable. Okay, so what I want to do is work another example. We'll come back to some logarithms. I've got another example here that I want to do. with the radioactive decay that I thought was a good example that I did yesterday during the conference hours. So let's look at some examples here. So let's see here, something interesting. Okay, so here's a nice example where we just create a polynomial. So in this particular example, we want a real polynomial. So real polynomial. We can call it f of x or p of x. I don't think it matters if you want to call it f of x. I think I use f of x notation on your test, but it doesn't matter. You can think of it as p of x. They're all functions. And let's see, the degree of f will be 4. And let's see, in this case, we want the following zeros. Let's say real polynomial f with integer coefficients. And so we have zeros. We've got a, let's see, a negative 3i. And we also have, in this particular case, let's see, what was the other zero that I wanted? Oh yeah, we want a 1 plus a 2i. This is just to give you practice with the occurrence of complex or imaginary zeros in conjugate pairs. So we have zeros of negative 3i and 1 plus 2i. And then this is going to be a unique polynomial. We want p of 0 to be 90. So this is actually going to specify a unique. In some problems, you just have a leading coefficient of 1. And of course, then the polynomial is not unique. So this will describe a unique polynomial. And let me just go ahead and use the same notation here, f. So this is going to be a unique polynomial. So now let me remind you of the lemma. And this is what you should use on the test because it's going to save you lots of time. I went over it. So if you have a real polynomial with imaginary 0, and I'll say imaginary 0, a plus bi, right there, imaginary 0. Then the quadratic factor, again, we don't want a polynomial with imaginary coefficients. We're specifying integer coefficients. Then the quadratic polynomial is, what is it? What is the quadratic polynomial that corresponds to this imaginary 0? Where I showed you in class, I've actually proved it. This is x squared minus 2ax plus a squared plus b squared. Now, of course, you can use the factor theorem and multiply all this out, but it's a common result. It's a standard result. And so it makes more sense to use this to move the problem forward. Like we don't want to have to derive the quadratic formula every time we use it. We don't want to have to derive the quotient rule for logarithms every time we use it. So this is a very nice utilization of the theory. So again, we can simply replace the a from the imaginary 0, that is the real part, and then of course the b part, which is associated with the imaginary unit, we just replace in the formula. So now what does this apply? So we've got the following zeros. So we'll have zeros, and then we'll have the corresponding factor. So again, I'm doing these. If you can do this, you can certainly do the factor a 0 of 1, that just gives you x minus 1. That's simple, but I want to remind you of this so you can use it as you test. So now, for instance, negative 3i, that's an easy one. Notice the a is 0, so this term is just a 0 term. So we get, in this case, the b is 3. If we square the negative 3, we get 9. So this factor is just x squared plus 9. Of course, if it were x squared minus 9, that would be plus or minus 3, the difference of 2 squares. So this is really what your intuition already tells you, but you certainly don't have to multiply it out. So of course, here a is 0. So here, let me just write to the side. A equals 0, b equals negative 3. So we just fill this in and we get this factor. Now let's try the next one, 1 plus 2i. Well, let me go ahead and to the side and say, okay, so a equals 1, b equals 2. So this gives us x squared. Now we have what? Negative 2 times 1. So that's a negative 2x. And then we sum the squares. So we have 4 plus 1, which is 5. So of course, if you work this backwards with the quadratic formula, then you get this. So this is the backwards problem, so to speak. We're not normally interested in going in this direction, but when we're trying to build polynomials, we don't have any choice in the matter. So now let's go ahead and put everything together. So this implies that f of x, our polynomial, again, we're calling it f now. Sometimes I've used the letter p, which is fine. We'll just have the leading coefficient, which will be a, and then we'll have x squared plus 9 times x squared minus 2x plus a 5. So remember, by the factor theorem, we can put both of these factors into our polynomial, because if we have this 0, we must have this factor. If we have this 0, we must have this factor. So we've got this, but then we've got that leading coefficient that we always have by complete linearization, the fundamental theorem of algebra. And so at this point, we might say, well, we can go ahead and figure out what the a is because we can easily substitute 0 here. So let's figure out what the a is. That is, in this problem, we need to do that because of the way it's structured. So we have f of 0 equals 90, but that's easy to do. So we have a, but notice all the x terms are just replaced. That is, each of the x's is replaced with 0, so they 0 out. So we get 9, and then of course here just a 5. So that's 45 times a. 45 times a. So of course, if we divide both sides by 45, a equals 2. So now we can now do a little column multiplication with the distributive law, and then hit everything with the 2 because we're lazy. So we say f of x equals 2. Now you're thinking, well, Professor Ron, if I write this down with the 2 filled in for a, that's a polynomial. But maybe what we're trying to do is figure out the descending form. Maybe the solutions are only given in descending order, and so we need to multiply everything out. So of course, this is a polynomial that's factored. So again, we're doing the backwards problem. So for right now, we've got this 2 out here. So we'll just kind of leave the 2 over here. So we'll just say 2 times and just go ahead and multiply out. So x squared times x squared is x to the 4th. Then we have x squared times negative 2x. So that's a negative 2x cubed. And then x squared times 5, just using the distributive law, 5x squared. Now we'll hit everything with a 9. So 9 times x squared is 9x squared. And just line up the powers. And then 9 times negative 2x, that'll be a minus 18x. And then of course, 9 times 5 is 45. So let's just add them up. So this will be 2 times, so we've got x to the 4th minus 2x cubed. Now we add these, we get a 14x squared minus 18x plus a 45. And now, of course, we can multiply by 2. So if and only if f of x equals 2x to the 4th minus 2 times the negative 2. So we get a 4x cubed. And here are 2. We get what? A 16 and a 1. So that'll be a negative 36x. And then 2 times the 45 will be a 90. Now, when you think about this particular problem and you look at what we've done, let's see here. Let's see if I've got all of my terms set up correctly. It looks like I do. And then the 2, 14. Oh, I left out my 14 squared term. Oh, sorry. Let me stick that in. I just ignored it. I thought it looked kind of odd. So here, of course, we have the 28, 2 times the 14. Don't leave out the squared term. And then we have the minus 36x plus the 90. There we go. So don't forget me. So we have 2x to the 4th minus 4x cubed plus 28x squared minus 36x plus a 90. And that takes care of everything. So what I wanted to focus on here is, again, if you have examples where you need to create a polynomial, of course, with integer coefficients, because that's pretty much what we do. I mean, there's nothing wrong with a polynomial that has imaginary coefficients or coefficients like the square root of 2. I mean, it's possible. I mean, for instance, I'll say a little bit more about this, but I just want you to remember as you can always use the formula sheets that are on a Blackboard, or you can make your own formula card, because I certainly allow you to do that. You have the flexibility of testing at home and you can have your notes. That's fine. That's really a luxury. I mean, I think sometimes the online classes are really a boost for the students, because I think we've lowered your anxiety by about 50%. But of course, everybody has a different way of looking at things. I just always remembered when I would go to a class for a test, there was a little bit of jitteriness. And then, of course, once I started taking the test, because I had prepared, I was fine. But just that little bit of time before you start, we're always a little on edge. So just remember the nice lemma here that says if you have the imaginary 0, then the corresponding quadratic factor is given this way. So you don't have to do the factor theorem and multiply all of this. That is certainly doable. But this is a nice result that allows you to move the problem forward and very quickly. And then, of course, when you multiply, you can line things up this way. That probably makes the routine a little bit easier. Just notice if you have a specific value of the function stated, then you do create a unique polynomial. If that's not stated, then it might be that you're just looking for a degree of a specified degree with leading coefficient equal to 1. So again, this problem has the added detail of having a specific value, which allows us to evaluate this leading coefficient from the complete factorization or complete linearization. So here's something that's important. When we go backwards, we have to chop it up completely into linear factors. A lot of you would like to put this as a complete linearized factorization, which is false. These quadratic factors are fine if we're trying to build, but this would have to be broken down into what x minus 1 plus 2i and x minus 1 minus 2i for complete linearization. So when you've got to chop up something, you've got to chop it up into just first degree factors, which again is something that's important, because the linear factors that way reveal all of the zeros. Okay, you don't always have to put in all the minuses, just so the linear factor basically says, okay, here's the zero if you look at it. Of course, if you put in all the minus signs by the factor theorem, then you can actually read the zero from the explicit linear factor. Okay, so this is an excellent problem, again, that covers a lot of bases. That's what I'm trying to do. I like to do problems that give you plenty of insight as opposed to a bunch of busy work. I'm not, the test is not full of busy work and simpleton problems. They're problems that are good foundational problems, problems that I know that I focus on in class that will allow you to have your success in your calculus sequence. Now, another good example, let's see here. Let's do, let's just practice the division algorithm. Say on the test, you're asked to divide two polynomials. So here's an example of division of polynomials. Now, of course, synthetic division is really nice when we're trying to check for zeros, and that's dividing by x minus c, and that's a special technique. We'll talk some about that. But when we just have division of polynomials where the divisor is not x minus c, we have to just use the standard long division. So let's try this. Let's see here. Here we go. In this particular case, we will have, let's see, I'm going to write this like I did in lecture. P of x equals 20x to the fourth plus 16x cubed plus 9x squared. That's P. And then the divisor, this is what Dr. Stewart uses, the divisor D will be 4x squared plus 1. And here's what we want to do. Here's what we want to do. We want to write the equation, and we're not going to write the quotient. We're going to spread it out. We're going to say P of x equals, in this case, the divisor times the quotient plus the remainder. Now, of course, you can always divide by the divisor and just have Q plus R over D. That's another form that we like to use when we're working with rational functions and we're trying to graph them. But again, here, this is the division algorithm. And remember, the degree of R is strictly less than the degree of the divisor. So this is the division algorithm. This is what we call the big hammer. It's a very important result. It gives us the remainder theorem and the factor theorem. So again, results like this are like, of primary importance. So again, we just do our long division. Again, this is degree 2. It's not an x minus c, so we certainly can't try synthetic. That would not make any sense. So we have 4x squared plus 1. And then we write the dividend, which again, in this case, will be p. So we have 20 x to the fourth plus 16x cubed plus 9x squared. And if you want, you can put in your placeholders for the x term and the constant term, just 0x and 0 if we need them, okay? So now when we divide, we just divide like we're dividing real numbers, just like we've got digits. What are the placeholders? The ones, the tens, the 100s, et cetera. Like I showed you when I introduced this. Hopefully that illuminated things a little bit. So we have 20x to the fourth divided by 4x squared. Well, the 20 divided by 4 is 5. And then, of course, x to the fourth divided by x squared is x squared. So again, when we start off, we say 20x to the fourth divided by 4x squared, which is 5x squared, okay? And then just in regular division of integers, we now multiply. So 5x squared times 4x squared, of course, is 20x to the fourth. We just proved that by the division process that we did. And then now we have 5x squared times 1. So this will be a 5x squared under the x squared column. We don't have anything to put here. And then the division process says we subtract, and then what's left over. So now, of course, here, the 20x to the fourth terms absorb, and we're left with the 16x third to the third power. And then, of course, here we have the 5 from the 9, which is a 4, so 4x squared. Now, of course, we check the degree here. This degree is 3, and it's larger than the divisor degree. So this restriction here says we keep going. So again, 4 into 16, that'll go 4 times. And then, of course, x cubed divided by x squared will just give us an x. So now we have 4x times 4x squared, which of course is 16x cubed. We just proved that by our division process. And then we have the 4x times the 1, which is 4x. So we move over here. Well, let me not move too far over. Plus 4x. And we subtract. Now, of course, bring down your plus 0x. That's where these placeholders are very important. They just align things for us. So now, of course, these absorb, and we have a 4x squared. And now we have the 0 minus the 4x, so this is a minus 4x. Now, of course, this degree is 2, this degree is 2, still not strictly less, so we keep going. So again, 4x squared into 4x squared, well, that's easy. That's just a 1. And then we multiply. 1 times 4x squared is 4x squared. And then, of course, 1 times 1, we can go ahead and put our plus 0. We get a 1. Again, subtract the division algorithm process that we learned in what, 4th grade? I don't know when you learned division, 5th grade. Who knows anymore? Everything is learned so quickly. So, of course, these terms absorb, and we're left with a negative 4. And then, of course, here we have a 0 minus 1, so minus 1. So negative 4x, excuse me, minus 1. Now, this, again, the degree here is 1, the degree here is 2. The division algorithm says stop, so we stop. This is our remainder. So now this implies that p of x, our original polynomial, is now d of x, which is 4x squared plus 1 times the quotient 5x squared plus 4x plus 1, and then plus the remainder, which again you can write this way in parentheses, plus negative 4x minus 1. So that way we mimic that exactly. So when you think about these types of problems and you think about the division process here, one thing I want to note is that when you, again, when you think about this particular process, I want you to go back to the lecture that I initially did when I was just dividing polynomials, where I replaced the x's with numbers. And then you saw that the process was really just the standard division algorithm for integers that you learn in number theory. So what I keep saying is that the number theory and the algebra coincide. And then, of course, the geometry is algebraic also. I mean, as we're doing trigonometry now, it seems like all we do is arithmetic. But there's a beautiful marriage between the arithmetic and the Pythagorean nature of the unit circle. Again, and then I get all these messages on WebAssign. You got to respect the arithmetic of the unit circle, the quadrants. What are the values? What plus or minus? I mean, it's just like it spins in your head. It's not overly difficult, but you just have to respect it. So here we can see in this particular case that d of x here, 4x squared plus 1, does not divide this polynomial because the remainder is non-zero. So again, we just look at this like we would be looking for zeros. But again, this gives us a formulation that is the standard formulation for the division algorithm. Now, of course, if we wanted to write it with P divided by D, we could also do this. Let me go ahead and write this to remind you. We could say, I'll go ahead and write out what P is. 20x to the fourth plus 16x cubed. Let me slide this up a little bit. Plus 9x squared. And now just divide everything by d of x, the divisor. Here's another form that's very useful that you had to do in your WebAssign. So now we have the quotient. So we would think of this, ladies and gentlemen, as a quadratic asymptote. And then, of course, we've got the rational part. So this is like when we do slant asymptotes, you have the asymptotic part here, and then, of course, the part here that eventually fades to zero. That's why the curve will start to approach this function. And of course, in the case of the slant asymptote, this is just a line, say a first degree. So again, this form here is very helpful when we're thinking about graphing functions that have slant asymptotes or the oblique asymptote. So of course, again, we can always take a result and modify it. And what we say here is exactly what we say here. So again, don't be afraid to adjust your result to push you to the next level. That's what we do in mathematics. We're always adjusting our outcome. We find that the sheer mechanics of doing math can be tedious at times, you know, keeping track of signs, keeping track of numbers and things like that. That's the pay your dues part. The fun part is where you can look back and say, well, I'm going to make this manipulation to make the problem provide more detail. So we think of solving a problem as starting with an equation and then simplifying it to the solutions and say, wow, of course, working back is like the process, the backwards problem that we don't like to do because that can be very difficult also. All right, so very good, division algorithm. Now what I want to do, you're pretty good with multiplicities and things. I like the fact that you took well to that as I introduced it, especially when we solved inequalities. So I've got an inequality here. I think there's one on the test just as a mode of review. So let's look at this. So this will give us a practice with multiplicities, computing zeros, things like that. Example. So we'll say solve in R. So we've got, in this case, x to the fourth minus 5x cubed plus 18x is greater than 0. Now, if you look at this and you think about basically what we're trying to do in this particular case is you consider what I taught you. I said, okay, BVs. Anytime we do a sign test, we can do the BVs, look at the extremes, and then think, okay, what are the multiplicities of the zeros? Do we cross or do we just touch? Like when you're graphing a polynomial, very straightforward. But if you just look at this polynomial here, you can see that it has a very simple structure. It's a fourth degree. There's no negative out here. So the end behavior is that it would always pass to infinity, so to speak. If you put in a negative number, the dominant term is still positive. So it will grow to infinity as x approaches negative infinity. And it will also grow to infinity as x approaches infinity, just using the end behavior. So in some cases, the multiplicity arguments do help us. For instance, if we know what happens on either end, we can always use the zero multiplicities to figure out cross or touch. So we're either above the x-axis or below to get a nice reasonable graph. Now, with that said, that lacks plenty of detail because we don't have the extreme values, which we would have to utilize calculus to uncover. So when you get to calculus and you define the derivative, you're going to look for places in the function where the actual tangent line to the function, if it does exist, is 0. And then that gives you an opportunity to assess the peaks and the valleys, the extrema of the function. Okay? So that'll be something that you will discuss in great detail in calculus, but you're going to take all of this with you and add to it. So now first, we think we need the BV technique, but beautifully here we have an X that we can factor. So we're thinking, well, let's just do it. So we have an X times X cubed minus 5X squared plus an 18 greater than 0. So now we already know that a BV in this particular case is 0, and that's a freebie. Now, let's face it, this is a luxury that we don't always count on when we're working with problems like this. So now, in order to get the other BVs, we've got this real polynomial here. And then we think about the fact that we look at this and say, okay, let's just check this out. Since it's degree 3, let's just kind of think about the disposition of zeros. So if we look at, let's just call this, we'll just give it a name as a sub polynomial. Let's just call it f of x. And let's just look at, I want to kind of look at Descartes with this. Let's look at the variation in f of x. Okay, so we start, so we've got positive, so we change, 2 changes. So we got 2 here. So the variation in sign of f of x, again, 1, 2. Start here, change, 2. So this implies 2 or 0 positive zeros. We don't have to say positive real zeros. That's redundant. Complex numbers aren't positive or negative. They're not ordered. So I'm not really sure why that sticks. But the idea is that Descartes says that we can look at the variation in sign, and that'll tell us how many positive zeros we could possibly have. This says that we either have 2 or none. Okay, well, let's go ahead and look at f of negative x just to review this. Remember, whatever number you get for the variation, you decrease by 2. Okay, as long as that number is non-negative, it makes sense. But if you decrease by 2 or 4 and you get a negative number, of course, that makes no sense. So Descartes is very useful. Just apply it in a common sense way. So now let's do f of negative x. So this is going to be negative x cubed. Of course, the cube will survive the negative. Of course, here in the squared term, that's not going to change because of the square. And then, of course, plus the 18. So again, remember when we replace x with its negative, the cube here will render the negative surviving. The square absorbs it, so this negative survives. And then, of course, the 18 doesn't change. Now let's look at this. Variation of f of negative x. Well, let's just start. No change, 1 change, 1. So this implies 1 negative 0. All right. So when we think about the disposition, let's just do it. We'll say plus, minus, and then we'll say imaginary. So for instance, if we had 2 here, that would give us 1 because we've got degree. Well, for instance, here we could, let me write it this way. Where in this polynomial here, let me focus here, not the original. So this is degree 3. I need to make that point. So this is degree 3. So now 3, that'll give us a 1. Again, degree 3, 3 zeros, no imaginary. Notice we couldn't have a 1 over here because the real polynomials, we know that the imaginary zeros occur in conjugate pairs. So we couldn't do just 1 imaginary. That won't work theoretically. Or Let's go here. Say we have the 0. Well, then the only possibility for the negative zeros here is 1, and then that would mean 2 imaginary. Okay? So when we look at this particular polynomial, we can have a disposition of zeros that matches 2 positive, 1 negative, or no positive, 1 negative, and 2 imaginary. That's it. Those are the only possible dispositions. So we're thinking, since this is an inequality, we're probably going to end up with that one. All right. So this is kind of just a walk down memory lane from Descartes. Again, if you have a Descartes problem on the test, all you have to do is analyze the variation, do this procedure, and you're done. You're done. Okay, that's a quick problem, but that requires that you know Descartes, you know the actual theorem. That's a quick problem if you know the theorem and understand variation. And I've tried to go through that in a way that would make it real for you. Now, let's look at this and say, okay, let's figure out which one we have here. Notice we always look at this and say, well, there's nothing really easy about this, because when we look at this, we see if we replace it with 1, we certainly don't get a 0. And then if we replace with -1, we don't get a 0. So the simple zeros aren't available to us. So if we look at this, we have a P over a Q, think rational zeros. So we've got what, unfortunately, plus or minus a 1, which we can kick out. Then we have plus or minus 2. Then we have plus or minus 3. And then plus or minus 6, plus or minus 9, and plus or minus 18. And then, of course, Q is just plus or minus 1. So now, when we look at this and we think, okay, what does this tell us? Well, that leading coefficient, what's the possible list? It's just the top row. So here's our list. And we know those are out. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, and plus or minus 18 is all the possible integer divisors of 18. Remember, 18 is 2 times 3 squared. And when you think about that, you have 2 plus 1 times 2 is 6. 1, 2, 3, 4, 5, 6. That's a number theoretic construct. And later on, when you get to the university, maybe you'll take some number theory. I took a graduate number theory class, and it was one of the most difficult classes I took in graduate school, but it was very illuminating. So now we're thinking, okay, let's find some zeros. Let's do our synthetic. So we've already seen that 1 and -1 don't work, so we're not going to even worry about those. So we have a 1, we have a -5, and of course there's no x term, so we have a placeholder of 0 and then an 18. So there is nothing, when we look over here, we're thinking we're going to look at this first line and say, well, maybe we should try for some of these positive zeros that we could possibly have. So we know plus or minus 1 doesn't work, or 1 doesn't work, and we can try 2 and 3 and move up that way, start with the smaller numbers. So let's test 2. So bring the 1 down. 1 times 2, 2 plus a -5 is a -3. And then -3 times 2 is -6, plus 0 is -6. And -6 times 2 is a -12, plus 18 is a 6. So, well, that's not a 0. And then, of course, these aren't all positive, so it doesn't say stop. Remember, that's not a very robust argument with the bounds, but at least gives us a reason to keep looking. So let's try 3. Bring the 1 down. Again, this looks a little bit more impressive. That's not a huge remainder. So we have 1 times 3 is 3. 3 plus a -5 is a -2. Then we have a -2 times a 3, which is a -6. A -6 plus 0 is -6. And there we have it, jackpot. 3 times a -6 is a -18, plus 18 is 0. So that's a jackpot. Now, what's nice about this is that what's interesting here is that since we got one positive zero, we know without a doubt that this cannot happen. This cannot happen. This must be the case right here. So Descartes does at least give you information that is useful. So now this implies by the factor theorem, and remember I called this smaller polynomial f of x, but we'll go back to the big one. So now we have the larger one. Let's just call the larger one p of x. So now p of x equals, I'm doing this problem and fleshing it out with the zeros, with the Descartes, with the bounds, all of that, putting it into one problem so that you can see the context of how all of this fits together. That's called learning, ladies and gentlemen. That's called synthesized learning. That is what I'm teaching you to do. I don't care about tricks here and there. I don't care about short, cutesy problems. They are useless. The way to do STEM is to be able to critically think. I'll be doing critical evaluation of critical thinking for the general education project. And then of course, we're gonna have a critical thinking exercise in this class. The idea is that as we learn to think and analyze, we bring our level of thinking to a higher level. So now we've got what? We've got x, we have x minus 3 by the factor theorem, and then we have the reduced polynomial, which is x squared minus 2x minus 6. And this is quadratic. So we say happy days because we know quadratic. So now let's look at this. So again, AC gives us a -6, and I don't think any of the factors of -6 will sum to -2. So let's look at the discriminant. B squared minus 4AC will give us a -2 squared minus 4 times 1, in this case times a -6. These are easy numbers, but of course, you know, I want to factor it. So this is 4 minus a 4 times a 6, right? So this is a 4, and this is a what? 1 minus a 6. So this gives us 4 times a -5. Now, when you look at this particular case, let's see here. We've got a negative, and let me check something. Oh no, let's see. Let me just check something here. So we got negative, we got 4, and then we got minus 4, A, and then the C, and then we've got, in this case, okay, this will be a plus. Sorry, that's a plus. We got minus minus, so that's a 7. Cool. So here, remember the minus minus is plus, very important. So now, positive. So back up here, we've satisfied this requirement again, in the sense that now what we see is two reals. So the quadratic formula will give us an additional positive and then one negative. So this implies that x equals the opposite of b, which is 2 plus or minus the square root of the discriminant. So that'll be 2 times the square root of 7. That's why I always write it this way, so we can easily see the perfect squares, dividing by 2a, which is 2. So now all the 2's absorb, and this gives us a 1 plus or minus the square root of 7. Now, of course, like I said before, x equals 1 plus square root 7 is clearly positive, and x equals 1 minus square root 7 is clearly negative. So again, we've justified the result of Descartes. We validated that Descartes has given us what we need. So now notice we have all multiplicity 1. So P of x equals x times x minus 3. We'll just do a complete factorization. X minus 1 plus square root 7, and then x minus 1 minus square root 7. So that's why I like this problem. These are problems from an old test that give you, each of the problems gives you everything you need to know. This covers everything about polynomials and then some. And so now this is our BB. So the BBs we're done. We've got 3, we've got 0, we've got 1 plus square root 7 and 1 minus square root 7. So we can easily do a sign test. So here we'll use this complete factorization. So now notice here that if we look at this, let's check this out. So negative, let me write it this way. Square root 7, let's just do a little analysis here. This will be between 2 and 3, okay? And so of course, now if we hit it with a negative 1, so we'll have negative 2 greater than negative root 7, greater than negative 3, and now add 1. So we'll say 1 minus 2 greater than 1 minus square root 7, greater than 1 minus 3. So if and only if we have what? Negative 2 less than 1 minus root 7 less than negative 1. So what we're seeing here in this particular case is that this number is between negative 2 and negative 1. So when we plot it, I mean, just to kind of give you a ballpark figure of where it lives. So we've got what? The 0 here. We have the number between negative 1 and negative 2, which is 1 minus root 7. Lots of times it's good to bound things with just elementary algebraic means. And then now notice, if you will, we've got the 3, and we can do the same thing here. Notice here, if I take this, add 1, we get what? 2 plus 1 is greater than 1 plus root 7 is greater than 3 plus 1. So 3 is a lower bound and 4 is an upper bound. So now we see that 1 plus root 7 is actually bigger than 3. So we can, again, 3, and then just slide it over, even though it's not very scale oriented. We know that this is an upper bound, so we have 1 plus root 7. So this gives us an order on the number line that's very simple, just using elementary methods, okay? So now, let's check the sign here. So we can just take like a negative 10. That's all we need to check, because these are all multiplicity 1, so the graph will cross at each 0. So here we check it out, we get a negative, got a negative here, 2 negative, well, again, when we're subtracting, again, this, we put in the negative and the negative here, that's still negative. And then when we put in the negative here, again, negative 10 is much bigger than that or much smaller than that. So we get 4 negatives, which is a positive. So again, when you think about this, we cross at all of these places. So above, cross, 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 cross. So this is just using multiplicities of 1. So at each case, we cross because of multiplicity 1. Cross, cross, cross. And that has everything to do with x minus 0. That's, again, that's a 1, a 1, a 1, a 1. Multiplicity equal 1 for all zeros. So you don't have to do much with your sign test. So now the original problem says, and we didn't multiply anything, we want this positive. So here, I'll use blue. We have a check here. X, 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 check, X, 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 check. So none of the numbers are included. None of the BBs are included because that makes equal to 0. So this implies, where does X live? So we have negative infinity to 1 minus root 7 union 0 to 3 union 1 plus root 7 to infinity. So what's interesting about this particular problem, and that's why I did it, is that it covers all the bases. When you think about this particular exercise, we start with an inequality, which is really a polynomial exercise. Remember that problem we did? We made the box and we figured out the possible sizes of the squares that we could cut out to produce a box. That was a good problem. And it reminds me of this one. That is, we had to figure out, okay, which values of X would make sense. And if it's a cubic polynomial, do we get 3, do we get 1, or do we get 2? And we ended up with 2 that were legitimate. The other one was too big. So once you look at the algebra, it tells you what to do. So now, of course, when we look at this and we think, okay, well, we've got a free 0, which is 0, and then we check this out. We tried Descartes to figure out the disposition of the zeros, at least to kind of give us some idea. I mean, it's the coefficients aren't all positive, so we can't just, eradicate the positive zeros. Descartes says you're either going to have 2 positive, 1 negative, or no positive, 1 negative, and 2 imaginary. But we quickly see when we apply the rational zeros theorem that the first case is valid. And so at that point, we look at the reduced polynomial via synthetic division here, that is, and via the factor theorem and synthetic division, we had the reduced polynomial, we have the happy face because we know about quadratics, and that gives us the remaining zeros, again, which validate our result from Descartes. And then, of course, we can get a complete factorization, all multiplicities 1, so we know we're going to cross at every 0. So all we have to do is just figure out the sign at one extreme and then cross. And you can check all of these if you want. I mean, on a test, you can always check things just as an additional way to validate things. But of course, go back and check this. And then, of course, the fact that we have all these multiplicities 1, we can save ourselves a little bit of time. So this problem is kind of like, I remember I did one like this before the first test. I always get excited about problems that give you all of this information that again bring your thinking to the next level. So again, this is kind of like your plunge back into the theory of polynomials, rational zeros theorem, Descartes rule of signs, bounds, multiplicities, all of that. And this, then of course, this would be a great way to graph. The graph comes exactly from this. So the end behavior, everything, all of this is covered in this problem. So at least, if you can do this problem, you're pretty much set for polynomials, right? And it's all bound up in an inequality. So sometimes we actually end up doing work that we don't expect just because it's germane to solving the given problem, okay? So now what I want to do is there's an example here from the practice test. It's just a good equation. We've done a quadratic form, but I want you to remind you of a technique that I shared with you about solving equations. And of course, you know how to use the log properties to combine and compress and expand. Those are very useful. Here's another example. 3 to the 1 minus x equals 7 to the 2x plus 3. And we want to solve in R. Now, of course, when you look at this kind of problem, and I did this two different ways, and in occasion, there might be a direction that says, express your answer in terms of natural logarithms. Okay, what I want to do is just change the base and then convert to natural logs. Now, of course, if you already see that directive, then you don't have to worry about changing the base. You can just apply the natural logarithm to both sides and forget that. So here's a little proviso that I'm going to add. Write the solution in terms of natural logarithms. So if I have that proviso in a problem I'm working, then I'm going to impose the natural logarithms from the very beginning. You know how to change the base for exponentials. I've taught you how to do that. But if the problem says write the answer in terms of the natural log, I'm going to start with natural logs to save some time for computation. So if this is the case, this would imply apply the natural log to the equation. And that just means use the power rule. And the power rule is the identity that allows you to remove the power from the exponential or power function to the front of the problem as a coefficient. So using this directive, we'll have the natural log of 3 to the 1 minus x power equals the natural log of 7 to the 2x plus 3. And then, of course, with this, I use the directive here of applying the power rule. So this will save us a little bit of computation time. So now, if we look at this, we have 1 minus x, which now the power becomes a coefficient, times the natural logarithm of 3. And then, of course, the power 2x plus 3 becomes the coefficient of the natural log of 7. And so when we look at this, we're thinking, well, this is nice and linear in x, so we can isolate the x's just by combining terms, very simply. So now we can multiply. So we've got, in this case, we've got what, a logarithm, natural log of 3, and then we have plus an x. We'll just go ahead and move the negative times the negative log 3. Just remove the negative by the log term. And then, of course, here we have a 2x times a logarithm 7, the power of e that equals 7. So this will be x times 2 natural log of 7. Just move all the numbers to the right. And then we have 3 times the natural log of 7. This is just cosmetic. It's like pushing all the stuff to the right. Normally we put it to the front, but there's more stuff here, so it's easier to navigate if you think of pushing all of the coefficients to the right. And now you're seeing that we can just remove the x's to one side and remove the non-x's to the other side. So this would be a quicker way to affect a solution, especially if the responses need to be expressed in terms of natural logarithms, or it could say expressed in terms of base 10 logarithms, whatever. So now we'll have x times the negative logarithm of 3. And now, of course, here, if we look at this, we take the x over. So this will be plus x times the negative 2 logarithm of 7. So again, we take this over, we get the negative and just put some negative into the coefficient. And now we have equals. So we have 3 times the natural log of 7. And then, of course, we subtract the log of 3 from both sides. And of course, if we have a bunch of negatives hanging out, we can always get rid of them. So now we can factor the x. This will give us a negative log 3 minus a 2 log 7. And this equals 3 natural log 7 minus natural log of 3. So again, we've got a very simple algebraic construct going on. We have a coefficient times x equals a number. So we can divide by this number. So x equals 3 log 7 minus log 3, all natural logs, divided by negative log 3 minus 2 log 7. Now, of course, this is a legitimate value for x, and it's legitimate in the original equation. But if you don't like all these negatives hanging around, you can multiply and divide by -1, which again will remove some of the negatives, but it's not required. But maybe you're looking at the answer choices and you see that you've got a more selective choice, which is eradicating the negatives. So now we'll have x equals, so again, this becomes positive, natural log of 3 minus 3 times the natural log of 7. And then, of course, downstairs, both of these negatives will be retired by that negative. So this will be log 3 plus 2 log 7. And so now when you think about this, what's interesting, at least in this particular case, and I don't think it matters one way or another, but notice sometimes when I work these problems, I'll just pick another base and run it through that way. But I want you to be aware of this type of construct. So now this would imply that a solution set would be natural log 3 minus 3 log 7 log 3 plus 2 log 7. Now, there was another example here that I wanted to do, an interesting equation. So again, this is always a good problem to understand. It comes up a lot in analysis and calculus, working with logs and exponents. Just a very valuable technique. Again, probably not as hard as the first problem we solved, but kind of intermediary. Now, the other type of question, I want to do like a half-life problem to remind you of the half-life and the cooling law, but this was a change of base problem with logarithms. So excellent example here. So this example looks like this. Again, solve in R. So we have, I got creative with the logarithm basis. So base 2 log of x plus base square root 2 log of x plus base 4 log of x equals 3. Again, it's always good to know how to change the base, even if you don't use it solving an equation on the test. It's certainly something that you will use many times in calculus. So now when we look at this, we're thinking, oh yeah, we're just going to put everything together with the product rule. But of course, that makes no sense because all the arguments are the same. So in order to push this problem forward is that we now, even if it weren't a nice problem like this, we need to change all of these bases, 2 of them, so that they mimic the other one. So since these are simple powers of 2, we'll just say change to base 2. It doesn't matter, but when you look at a problem, you're just interested in, like, for instance, if you're doing a WebAssign problem, you're interested in the quickest way to the solution, or at least an efficient way. And then, of course, the computer algebra system can check, it scans it and says, is this equivalent to the solution that we have encoded? And it checks it, boom, it is. So when we change this to base 2 and this to base 2, that's a simple exercise. So if and only if we have log base 2 of x plus log base 2 of x. And now, of course, we have log base 2 of the square root of 2. So again, the new log base of the old, plus log base 2 of x divided by log base 2 of 4. So again, I've done a problem like this in class, but it never hurts to see it again. And then, of course, now you're going to look at it differently, just like that problem with the rational zeros and the multiplicities and the Descartes. Now, hopefully, it's bringing you to new illumination. I think that the issue here is, again, synthesis. So now we're thinking, all right, this is just going to give us some coefficients, which we can easily compute. So we have log base 2 of x. Now, of course, square root of 2 is equivalently 2 to the 1/2. So we see that the base 2 logarithm of 2 square root of 2 is just what? 1/2. So we have log base 2 of x divided by 1/2. And then plus, well, of course, now we'll just say 4 equals 2 squared, like we did in the other problem. Simple, but very important in this problem. So the base 2 logarithm of 4 is just 2. So now we can factor all these coefficients. Well, first, we've got a common factor of log base 2 of x in all of them. So let's factor that. So we've got a 1. Now, of course, we have a 1 divided by 1/2. And we have a what? 1/2. And this equals 3. So we have log base 2 of x. So of course, 1, the reciprocal of 1/2 is 2. So 2 plus 1 is 3, plus 1/2 equals 3. So now, if you will, this is just 6 over 2 plus 1 over 2, which is 7 over 2. So we have 7 over 2 times the base 2 logarithm of x equals 3. So now we'll just solve for base 2 logarithm of x. This will just be, in this case, 3 times what? 2/7, which is 6 over 7. So now when you look at this, you're thinking, what's a logarithm? It's the power of the base. So the power of 2 that equals x is 6/7. So if and only if x, well, let me not write the x again. If and only if x equals 2 to the 6/7 power. So now we have, of course, legitimate. Again, that's a positive input, so that at least does have a solution. So 2 to the 6/7. So that's a good example of at least a method of again, changing the base. Changing the base with logarithms is more complicated than changing the base with the exponential, even though I think it just matters on the actual type of problem you're doing. But when we look at this test, we see we've got polynomials and how they react to certain constructs like building a box or solving an inequality. And then we have logs and exponents. And we learn how to solve equations with those particular objects using their properties, mainly their identities in the definition of logarithm. Now, the last example I want to do is a half-life problem. And I thought this was interesting because this was asked yesterday during the office hours. And so remember, we did the cooling law, we did growth and decay. So this was an example that I did during my office hours, conference hours, and we had a radioactive sample, radium, excuse me, 221, and it has a half-life of, well, this is really short, so I thought this was an interesting problem, 30 seconds. Not like carbon-14 that has a half-life of, 5,600 years or something, that's what the archaeologists use. And then we have, so compute the time for 97% of the sample to decay. So again, we've got a sample, or maybe, we've got something that's infused with radium, and we just want to figure out if 97% of the sample decays, how long does that take? And the key to this problem is interpreting the hypothesis. If 97% of the sample has decayed, this implies, well, how much is left? 3% remains. So that's imperative. Because remember, when we do these problems, we're trying to figure out, if we have this particular quantity of the sample, what T corresponds to that. So this is very important. This is extremely important. So now we think, okay, so we will say Y sub 0 corresponds to the initial mass of radium, 221. So this implies, or equivalently, Y equals Y sub 0 e to the KT. So now, using the half-life, and this will all be in seconds, we have 1/2 of the original amount equals the original amount, e to the k, raised to the 30. Again, I always have you solve for e to the k, and you'll need to do that on the test so you get nice, clean answers. Otherwise, your answers will be off, and that's not how I taught you. So, of course, the Y sub 0 is absorbed. And so now we get 1/2, which you can conveniently write the 1/2 as 2 to the negative 1. And that's just e to the k raised to the 30. Now, in order to solve for e to the k, we just do the 1/30 power of each side. So equivalently, e to the k will equal 2 to the negative 1 raised to the 1/30. And now use the laws of exponents. So this is 2 to the negative 1/30. So that's e to the k. So now this implies that we can rewrite our solution curve as y equals y0 times 2 to the negative, again, raised to the t power, t/30. So again, when you have the value for e to the k, you just multiply the power, in this case, times t, and that gives you negative t/30. So this gives us a nice, neat equation right here. And now this is our solution curve, which will allow us to solve for t, because we now know that 3% of the original amount remains. And that's where we need to find the corresponding t. So this implies solve the following equation. Again, this is just like what we did before, but this is not a very busy problem. The cooling law is probably about the same amount of busyness, but the half-life is kind of set up neatly for you. So here we have 3%, which is 3/100 of the original amount, will now equal our solution curve, which is y sub 0 times 2 to the negative t/30. Now, of course, the y sub 0's absorb. So this will give us 3/100 equals 2 to the negative t/30. Now, this is where it's convenient, ladies and gentlemen, to just use the natural log, because if we need an approximation, we've got a natural log that Google uses, that base that they use, or maybe the problem will just say give an exact answer. I mean, or maybe the problem will reduce to a nice exact answer, but I don't think it will here. So we'll just apply the natural log. So this will give us natural log of 3/100 equals the natural log of 2 to the minus t/30. Of course, I went ahead and did this in 2 steps, so now we can bring the power down. So this will be t, and of course we've got t/30, so let's just move the negative into the log 2/30. So we bring the negative t/30 down, and then we've got the 30 downstairs, the log 2 upstairs, and just move the negative into the coefficient, just like I've done many times. So now we've got a number times t equals the natural log of 3/100. So we can easily solve for t. So t equals, so we're going to invert and multiply. So we get log, well, let me, a little more space here so we can move the 30 upstairs. So we've got 30 times the natural log of 3/100 divided by negative log 2. Now, if you want, you can just go ahead and move the negative upstairs. So negative 30 log of 3/100 divided by log of 2. Now, when you look at this, this is exact. So you know, on the test, I may say, okay, very good. Here's an exact time. And the test may say, okay, round to the nearest integer. Okay. So this is what I've said before. I may set it up where I ask you for the exact expression, or I may set up where you take your exact expression and use your Google calculator. But notice, again, no approximations throughout this, all exact computation. And so now we're thinking, well, let me find Google. Let's see here. Let's see, stay stunned in there. So let me find my Google. Let's see here. Let me move this down. Okay, Google. Okay, so let me move this back up. So stop share. See if it can find it. Oh, good. It usually has trouble finding Google. So now we can just go up here and we'll use our parentheses. So we have negative 30 times natural log of 3 divided by 100. Very, very nice calculating device. We're certainly spoiled. Divided by natural log of 2. And this gives us 151, approximately 151.766681. And then, of course, in this case, we can just round to the nearest integer, which will be, let's see, 152. So this will give us 152 seconds. Now, again, what's important here, is what app? Oh, you know, kids, what does Professor Ron do? Let me show you. Use the Adobe Scan. Let me show you. See on my right here, let me get rid of this. See this Adobe Scan? I have an Adobe account, but the Adobe Scan is wonderful. So say I finish my work on this page. Say here's, let me just do a little example. Here's this page and this page, and let's see, I got this page and I got this page. So these are my test work for my test. Okay, here's how simple this is. Oh, died on me. There's Professor Ron and let me show you. This Professor Ron, that's my sister and that's my brother-in-law. We call each other the Three Musketeers, because we've known each other forever. My brother-in-law is like my brother. I have an older brother, but Hans is like my brother. Like I say, I've known him forever. So now what we can do, you turn on your Adobe Scan and you just line it up like that. Takes the picture. Move to the next one. Now, don't hit anything. It's got this picture in. Now you're going to hit continue. Let me move this up. Continue. Line it up. Take another one. Done with that one. I showed this to another student. They thought, wow, this is so easy. Now hit continue. Line it up. It does all the work for you. And this is what I use to post things on Blackboard. Do the last one. Line it up, and it'll take the picture for you. Now, when you're done, what you can do, and of course, I would delete that one. That one didn't come out. I'll have to take that again, so I'll delete that one. So now what you do, you got the picture here. So you hit your rotate to put it right side up. This one, you rotate until it's right side up so Professor Ron doesn't break his neck trying to read your stuff. Rotate. And then once you have everything, see, notice you've got all these clean scans. All these clean scans, and then you save the PDF and you put it wherever you want. I'll usually put mine in Dropbox, or you can save it on your phone, and then you're good to go. This is so easy, and you get beautiful, beautiful scans, okay? And the thing is, some of you, I'm not displeased with what you all are doing now. It's excellent. I mean, I get good pictures. If you just take a picture and then combine your pictures into one document, that's fine too. I've been able to see everybody's. Occasionally it may be a little fuzzy, but I can read it. The only thing is that when you take the picture, just put one picture per photograph, one sheet of paper, and then I can easily see it. The problem is that if you try to put two or three and it's back too far and then it's blurry, I can't read it. And if I can't read it, you're not going to get any credit for it. So the Adobe Scan, ladies and gentlemen, is nice. And so again, you should try that. Now, some of my students, I noticed they use Cam Scanner, and that I think is like a free app at the Google store. That gives a really good, nice quality output. So I haven't been displeased with anything. The only thing, just make sure if you take a picture and you append them all together, look at them. Once you make your file, ladies and gentlemen, open the file and say, okay, this is what I'm sending to Professor Ron, and look through it. Oh, that's real clear. I can see that. Oh, that's a good one. Oh, wait a minute. That one's blurry. I need to take that one again. So go back in and rescan. But you open your file once you've made it, and you look at it and you say, can Professor Ron read this? I mean, when I do my lectures, this is like clear as a bell. Okay, so I just need to be able to read it. It doesn't have to be perfect. It can be a little sketchy and a little fuzzy, as long as, sometimes you get extra stuff, but as long as I can read the notation, I can follow your work. I mean, I'm not picky. I just need to be able to read it. If it's blurred, or if you write so small and it's blurred, it just looks like a bunch of dots. Okay, so think about this when you're doing it, but again, before you send me the file with the Turnitin, just check to make sure that you can see it. You open your file, just check it out and make sure that it's good. Again, I appreciate this, but it is germane to legitimate work. And before I go, I want to remind you all to go to, here, let me just do this. Go to Blackboard. Let's see, let me find this. Let me move this over. I tell you, Zoom is crazy. Okay, let's see here at Blackboard. Okay, I remind all of my students about this. I'm going to go to Course Home. Here we go, right here, folks. SJC code for academic integrity and honesty. Integrity is one of the core values of San Jacinto College. As such, students are expected to exhibit honesty, integrity, and high standards, words I use every day, and freedom from lies and fraud in their academic work. If you send me a scan that I can't read, that's fraud because you're misrepresenting your work, okay? Personal integrity is important in all aspects of life, and students must conduct themselves in an ethical manner, both in and out of the classroom. Incidents of academic dishonesty will not be tolerated, and students guilty of such conduct are subject to disciplinary consequences. Again, do not use websites that work problems for you and copy the solution lines that they furnish. If you do that, I will know it and you will get a 0 on your paper. I only say this, ladies and gentlemen, because I see occurrences of it. And I'm not here to put you down. I am here to raise you up, but you've got to do your own work. And that's why I insist on a clean scan of your work. This is only to make your grades legitimate. San Jacinto College has a high academic philosophy. And when you get a degree from San Jacinto College, it carries weight, okay? It's different from other schools. And because of this academic philosophy, if you ever have time, you should have a conversation with Dr. Williamson. She is our college president. She is a PhD in English. She is a smart, smart person and does an effective job at maintaining the standards of this college. I salute her every day that I work at this school. And I want your grades to mean something, okay? So remember, as you do your work, you do it with integrity and honesty, and you own it, okay? You own it. That way, when you go through life, everything you do, you have your signature on it and you stand behind it and you make yourself better. Don't worry about X, Y, and Z around you. You worry about doing your work to the best possible potential. That's all I'm asking for you to do. Okay. So enjoy taking the test. I'll be at my office hours today, my conference hours. I'll send out invitations. I appreciate your attendance today. I know this was optional, and I'm sure some of you were bored by what I did because you're, 10 years ahead of everybody, which is great. But I hope that it was helpful to some of you to help assimilate things. So again, if I see you at office hours, that'll be terrific. Remember, I also have one tomorrow morning. And if not, have a wonderful, wonderful break. Get some rest, but do some math. Also, don't just go cold turkey and don't do anything. Take the time to do some review, to work into your trigonometry. Professor Ron loves that trigonometry, and it's great stuff. You will enjoy it too. So everybody have a great day. Thank you for your attendance today, and may the force be with you. I guess, and thank you. Have a good break. I will try to. I think we all need one. We all need a good break. So everybody have a great day. Thanks again.